Okay, so now I want to talk about a mechanism that competes directly with the SN2 substitution, and that's the E2 elimination. So if I were to sum the entire reaction up in one sentence, what I would say is this. I would say an E2 reaction happens when a strong nucleophile reacts with an inaccessible leaving group. Okay, I'm just going to stop right there for a second. Okay, so if you remember back from what we learned about SN2, there's a little bit of a similarity there. Can you guys tell me what condition is similar to the SN2? The nucleophile. Remember that in an SN2 mechanism, you needed a strong nucleophile to start that backside attack. Okay? Same thing with E2. We also want a strong nucleophile. Where the difference comes in is the leaving group. Remember that if you had a very accessible leaving group, what would happen? Backside attack. So remember that backside attack was favored when you have this very accessible leaving group, okay? Or very accessible backside. Well, for E2, we prefer an inaccessible leaving group. What that means is that these molecules are going to be bad, generally bad at doing a backside attack, so they're going to prefer to do something else instead, all right? So what is that other thing? What they're going to do is beta elimination, okay? So elimination of a beta proton, we're going to talk about that in a second, all in one step, okay? So let's go ahead and get started. Let's just start the mechanism off, and you guys tell me where you think the first arrow is going to come from. Maybe you don't know where it goes, but at least you should be able to tell me where it starts. And that's right, it's going to start at the negatively charged nucleophile, just like it did for SN2. Because this is a strong nucleophile, so it's going to initiate the contact first, all right? So I'm coming over here, and you'll notice that I have this nucleophile that wants to do, it sees this alkyl halide, there is a very strong dipole there, there's a partial positive right here, and this nucleophile wants nothing more than to give its electrons directly to that positive charge, okay? So actually don't draw what I just drew yet, I'm just trying to guide you guys through the process, all right? The nucleophile wants to donate its electrons to that positive, but there's a problem. The problem is that if you'll notice, count that carbon up, what you're going to notice is that this is actually a tertiary alkyl halide, okay? Do you guys remember what I said about tertiary alkyl halides? Do they have a really good backside? No, they have a terrible backside, okay? In fact, it's impossible to get through, okay? Just cannot get anywhere close. So now this nucleophile is frustrated. It's like, well, I'm a strong nucleophile, I want to do backside attack, but I can't. So what am I going to do? Well, instead it says, okay, instead of acting like a nucleophile and donating my electrons, maybe I can act more like a base. And the way that that bases act is that they are proton acceptors. So it's saying, you know what? It's too difficult to do this backside attack. So instead, let me just pull off a proton, okay? And by pulling off the proton, maybe I can donate my electrons that way. So we're going to go ahead and erase this arrow, and that's not actually going to be what happens. What happens is we're going to look for a beta hydrogen that we can take off with my nucleophile as a base, okay? So how to find beta protons, just to remind you guys, would be that this is my alpha carbon. The alpha carbon is the one that's directly attached to my alkyl halide. And then a beta carbon is any carbon that's directly attached to the alpha. So this would be beta, this would be beta, and this would be beta. All of those are beta carbons, okay? Because they are carbons directly attached to the alpha, all right? And then any hydrogen that's directly attached to a beta carbon is considered a beta hydrogen. So what that means is that I have 3 beta hydrogens right here, and we might have other beta hydrogens on those R groups, but the R groups are general, so I don't know how many H's there are or not. So the only ones that I'm given here are these 3. Does that make sense? So those would all be beta hydrogens because they're hydrogens directly coming off of the beta proton. Coming off the beta carbon. So, like I said, we're going to pull off a beta hydrogen instead. Let's go ahead and draw that the nucleophile attacks that hydrogen right there. Okay? Now, is that hydrogen happy with that mechanism? Can I just leave it there? The answer is no. I cannot just leave it there because hydrogen only wants to have 1 bond, and now it has 2. Okay? So if I make that bond, I'm going to have to break a bond. And this is the interesting part. We're going to take the electrons from the bond, from the carbon to the hydrogen. We're going to give those electrons to that single bond. Basically, the bond in between the alpha and the beta, okay, is going to get a double bond. So alpha double bonded now to beta carbon, okay? So now I have a double bond there. Is that the last arrow? Actually, it can't be because this alpha carbon had 4 bonds already, And now by making a double bond, it would have 5 bonds. So if I'm going to make that bond, then I have to break another bond, and the easiest bond to break is the one for the leaving group, because remember, the leaving group is going to be stable after it takes off, okay? Relatively stable. So let's go ahead and draw our transition state. What our transition state is going to look like is like this. So I'm going to draw everything that didn't change in the reaction with a solid line. So what that means is that I would have an H in the front and an H in the back, that nothing ever changed. I would also have an R in the front and an R in the back that never changed. Okay, so those are the things that, like, during the course of the reaction, nothing's happening to them. But what is changing is that a bond is being broken and destroyed at the same time between the H and between the leaving group. So the reason I drew it with partial bond is because this is a one-step reaction, right? So what that means is everything's happening at the same time. The H bond is being broken, the double bond's being made, and the leaving group is leaving, all at the same time. Awesome, okay? Now, there are too many bonds here, so there'd be a negative charge distributed throughout. I'm just going to write the negative on the outside. That just shows that the entire thing is negatively charged, okay? Because we have one too many bonds. And now what I want to do is show you one more unique thing about the E2 mechanism in particular, okay? This only has to do with E2. And what it is that if you were to take a Newman projection of this transition state. Now, I know it's been a really long time since we talked about Newmans, so try to unbury that information. I know you had already buried it or whatever. So try to think about a Newman projection. Remember that that was a way to visualize single bonds. So here's my eyeball, and if I were looking down the center of that bond, what would I see? Well, what I would see is that on the top I have two H's, okay? And what do I have coming off the bottom? The bottom, what I would have is a partial bond to an H, okay? Then what would I get in the back? What I would get in the back is I have those two R groups, right, with single bonds, so RR. But then on the front, I would have a partial bond to my halogen, all right? So there you have it. That's what the transition state is actually going to look like, okay? And the unique thing about E2 is that the transition state will always look like this. It's always going to have that conformation where my X and my H are as far apart from each other as possible. Do you guys remember what that conformation is called? Remember, that's 180 degrees apart, and 180 degrees apart equals anti. Okay? So it turns out that whenever you have an E2 elimination, because of what's favored, the way that it's favored, it's only going to react once the X and the H are perfectly anti to each other, or 180 degrees apart. And later on, I'm going to teach you guys how that's really important in predicting products, okay? But just to let you guys know, these two H's that I drew at the top would not have actually been able to react unless they rotated down into the anti position. So really, even though I said that I had 3 beta hydrogens, in this reaction I only had 1 that was in the proper position to be eliminated, all right? Cool. Don't let that get you too confused because, like I said, we're going to have an entire section dedicated to this one thing about the anti, okay? So then what would the product look like? Well, we know that the H gets removed, okay? So I'm just going to, like, chop it off, even though this isn't part of the transition state, but you're going to chop off the H. We also know that the X gets removed, right? So what you get left is just a double bond in the middle with H's and R's on both sides. So that's what my product would look like. It would just be a double bond with 2 H's on one side, okay, and 2 R's on the other, okay? And that is an elimination reaction. What I just did was I took 2 sigma bonds. This was a sigma, and this was a sigma, okay? I destroyed those bonds, and I made a new pi bond. And that's the definition of elimination. You take 2 sigmas, and you make 1 pi, all right? Awesome. Other things that I would get are just my leaving group, and then my nucleophile with an H on it. All right, easy.